Hello everyone, my name is Xiao. Today I'm going to present the paper iHunter, Hunting the Privacy Violations at Scale in the Software Supply Chain on the iOS platform. This is a joint work between Indiana University Bloomington, Peking University, and Alibaba Group. I'm the co-first author with Dexin Liu. So as we know, privacy violations in the mobile ecosystem is a growing concern for the users, developers, and regulators. So many applications collect and misuse personal data without proper privacy disclosure, which leading to a significant privacy risk. So in the literature, privacy research on the Android privacy is quite extensive, probably due to the availability of various off-the-shelf tools. But the same cannot be said to iOS. Although iOS is making up a larger share of the market, mobile market, studies focused on them are still quite limited. So as a result, there is a significant gap in our understanding of the privacy in the iOS ecosystem. So in our study, we will focus on iOS, specifically to the third-party SDK. So those SDKs are invaluable to the developers because they provide ready-made functionalities, making the development process faster and most cost-effective. However, this convenience comes at a cost. Many SDK introduce significant privacy risk, often collecting data in a way that are not fully transparent to either the developer or the users. Probably this is one of the main reasons why the Google data safety section are not that compliant. And however, existing research mainly focus on the privacy issues at the app level, not digging deeper into the role that the third-party SDK plays in those problems. So in our study, we performed a systematic study on the privacy violations in the iOS SDK, whose privacy disclosures are not that transparent. So however, fully investigation on iOS SDK present a few challenges. First, unlike apps, the SDK cannot be analyzed dynamically because they do not have entry point and cannot be executed the same way as the app. Besides, traditional static data flow analysis tools for the binary cannot handle the semantics of Apple's unique Objective-C and Swift language. Third, mapping the privacy-related data to the iOS framework API is another key challenge. So iOS has a vast and complex API landscape. And identify which API handle the sensitive data is not that straightforward. So to solve those challenges, we designed and implemented a tool called iHunter, which can detect various privacy violations from the third-party SDK. So from the high level, our approach relies on extracting the data flow statically from the SDK binaries and assessing the compliance with their respective privacy disclosure to identify any non-compliant SDK. So in particular, the design of the iHunter has three components. The first is semantic knowledge extraction, and the second is TIN analysis, and the third is compliance check. So for the semantic knowledge extraction, so our approach uses NLP techniques to pull out the key information from the iOS API documentation, like the tint source, tint sink, and the tint propagation rules. So those kind of semantic knowledge is essential for building a data flow graph that we used for our tint analysis. And further, armed with those semantic knowledge, our tool will employ under-constraint symbolic execution to construct the data flow graph. And further, we will extract the tint trace from the source and to the sink within the data flow graph. Each identified tint trace will represent a unique data flow, showing how the privacy data moves, whether it is being accessed, being stored, or being transmitted. So the third part is compliance check. Once we have mapped out those tint traces, we need to compare them against the privacy disclosures of the SDK. So we use a set of consistency model to spot any non-compliance SDK which do not follow the privacy laws or regulations, or they mispresent their data practice. So for the semantic knowledge extraction, we start by collecting Apple developer documents to gather the public API specifications. We will extract some key information like the return values, function description, parameters, etc. And to identify the data flow involving the privacy data, we first need to establish a set of sensitive system API which served as the tint source. So we classify an API as a privacy sensitive if its return value matched the privacy terms within a privacy data ontology. So privacy data ontology is essentially is a graph of the privacy terms that's defined in the legal document, like the privacy policy and term of use. So additionally, we manually investigated the iOS framework and popular third-party network SDK to identify the network API that will transmit the data out of the device, and some storage API that keep the data on the device. So those kind of API will serve as the sync API. Third, to automatically generate the tint rules. So we use a dependency parser to extract the semantic information from the API description. So this can allow us to infer how data propagates between parameters and return values. So to perform the tint analysis on iOS SDK, so we start by using Ghidra to disassembling and decompile the binary code into an intermediate representation, short for IR. Next, we will construct the control flow graph from the IR to map out the flow between basic blocks in the code. And further, we then use a customized under-constraint symbolic execution engine to create the loop and the function summaries. So those loop and function summaries capture the essential details like the data flow, transmission, and the symbolic value types. So using those summaries, we further applied a rapid backward slicing approach to resolve the dynamic calls. Once all the dynamic calls are resolving, we can refine our data flow based on the tint rules we extract from the system API. So once we have built the data flow graph with the source and sync API we collected from the semantic knowledge, we then able to extract all the tint traces from the data flow graph. So for each tint trace that carry sensitive data, we will further perform the compliance check to detect any violations. So iHunter defines 3 types of privacy violations. The first is the SDK processing the personal data without a available privacy policy are labeled as a non-compliance type 1. So to detect such non-compliance, we're using the existing tool policies, which can fetch the privacy policy by input the SDK official website URL. If the SDK do not have an official website, we further examine the SDK README file if they provide the privacy policy link. For the non-compliance type 2, so SDK displaying any inconsistency between their code data collection practice and disclosure in their privacy policy are labeled as non-compliant type 2. So we're using polycheck to extract the data action from the policy and then compare with the tint trace we extract to identify if there is any omission or incorrect disclosures. So for the non-compliant type 3, so SDK that illicitly obtain data from other victim SDK and hence violate the term of use of those victim SDK are labeled as non-compliant type 3. So we use the Xfinder to extract the condition under which data items are restricted by the term of use, and then check whether the tint trace from the caller SDK complied with those requirements. So in total, iHunter identified 2,585 non-compliant SDK out of over 6,000 iOS SDK. So this result highlights the significant issue of the non-compliance, especially in the iOS supply chain. So the majority of those non-compliant SDK are hosted on the CocoaPods, which is a dependency manager for the Swift and Object-C project. So in the following, let's break down the types of non-compliance. As we can see, the type 1 violations make up the overwhelming majority. Those SDKs access, store, and transmit user data without provide any privacy policy, which directly violates the transparency requirement set by the privacy laws. Among those 244 SDK that do provide a privacy policy, we found 58 of them had data collection practice, but did not align with what their privacy policy state. So this include a case where the data was either omitted or in the policy or disclosed incorrectly. And lastly, we also observed 45 SDK engaging in closed data harvesting. They're pulling data, the SDK pulling data from 15 victim SDK. Most of the victim SDK are well-known social network platform like the Facebook. So they are a valuable target for the SDK to harvesting the data. So we also examined the real-world impact of the non-compliant SDK by analyzing how the privacy violations propagated into the app that integrated them. So when developers use the third-party libraries that collect personal data, the app developers still remain the primary data controller and are responsible for ensuring that users are fully informed through either the privacy policy or privacy label. So here is some statistics. So our iHunter detected over 2,000 non-compliant SDK with 694 of them transmitted data out of device. Those SDK have been integrated into more than 15,000 apps, which make up almost half of the top-tier apps we analyzed in the Apple App Store. We then analyzing whether those app privacy policy accurately disclose the third-party data collection practice. Our finding shows that 28.6 of them are non-compliant. Those non-compliant practices are actually reflected in the app, leading to their own non-compliance with the privacy policy. Additionally, we investigate how those non-compliant SDK affect the accuracy of Apple privacy label. We reviewed over 1,000 apps, and we found almost half of them failed to disclose those privacy policy. So as we can see, those non-compliance SDK integrated into the apps can significantly lead to the app's non-compliance, eventually will pose a privacy risk to the end users. So here is a few takeaways. So we created a mapping between the iOS system API and the privacy-related data. We developed a static data flow analysis tool specifically targeted to iOS binary. We perform a large-scale analysis of iOS SDK non-compliance. We conduct detailed case studies. If you are interested, please check out our paper. And this is the end of my talk. Welcome to any questions.